Hey there, folks. I hope you've all had a great weekend. Here's a problem that involves a spring-loaded block moving up an incline plane. The block starts at the bottom, which is referred to as point A. Then 6 meters up the incline at point B, we're given the speed. What we need to do is solve for the initial elastic potential energy that was stored in the spring using all the information that was provided here. Let's start out by using trig to get the final height of the block at point B. We can use the same strategy from some of our previous problems by grabbing the definition of the sine function. In this context, y is the final y value of the block, r is the displacement distance along the incline, and theta is our 30-degree angle. If we multiply both sides of this equation by 6 meters, we now have the final height of the block in terms of quantities that we know. In addition to the final height, we're also going to need a free body diagram. Let's draw one with the block in the same position up at point B. The forces acting on the block here are its weight, the normal force from the ramp, and the force of kinetic friction, which acts opposite to the block's movement. Remember that since the weight doesn't lie along one of the axes, we'll need to break it up into its cosine and sine components. Now we're ready to start working with energy conservation. Here's our expression, and I'm going to eliminate the initial kinetic energy since the block is motionless before being launched up the incline. With that done, the goal now is to plug some definitions in and solve for the initial potential energy of the spring, U sub I. Let's start on the left side. The other work done on the system is due to the force of friction acting over the block's displacement, and that's negative, since it's eating away at the block's energy and reducing its speed. On the right side, the kinetic energy is our familiar 1/2 mv squared, and the final potential energy will be purely in terms of potential energy of position in the form of mgy, since we were told that the block is no longer in contact with the spring. Let's plug all that in and move the work done by friction over to the right as well, which will turn it positive. We know that the force of kinetic friction is defined as mu sub k times the normal, so that'll go in next. From our free body diagram, we saw that the normal force from the ramp balanced out the cosine component of the block's weight as it moved up the incline. So we can replace n with mg cosine theta. And I've kept the cosine portion here at the end so that we don't lose the displacement variable along the way. Since there's a factor of mass in each of these terms, we can take that out to shorten the expression a little bit. The same can be done with g for the second and third terms inside the parentheses, like this. There's nothing left to simplify, so let's go ahead and plug in some numbers. It's a little long, but if you do it right, you'll get the same result that the author of this book gives as an answer, approximately 119 joules. That's it. Problem solved. Thanks for watching, everyone.